Hello, my name is Bojan Mitov, the president of Mitov Software, and in this session we will cover developing multi-thread applications with Delphi and C++ Builder. Since probably most of the listeners are Delphi users, all of the demos in the session will be in Delphi. However, C++ Builder code will be included in the downloads available after the session. What is multithreading? Multithreading is executing multiple threads or functions at the same time within the same process. The multithreading can be real, when we have available multiple processors or cores, or it can be simulated on a single processor through using time sharing or switching the processor between different threads over time. What is a thread? A thread is a thread object or virtual processor which has its own stack and a function which this virtual processor will execute. In a single thread application, we can simulate threads by calling process messages or implementing complex event-driven state machines. Neither of those approaches is as efficient as using physical threads, and they should be avoided whenever possible. Why we should use multithreading? Multithreading is used whenever we run long processes and would like the user interface to be available to the user, or when we are waiting for slow hardware or process to complete and we would like the main application to continue operating normally. Why we should not use process messages? Process messages creates the danger of infinite recursion, where inside event it is called and the event is fired again by mistake. It also prevents the application from closing, as we'll see in one of the demos. It executes slower than multithreading, and it often creates more complex code than if the application is designed as multithreading application. There are a number of multithreading myths. The first is that multithreading applications are slower than single-threaded applications, especially on single core. That is not true, since in order to achieve the same type of functionality in a single thread, you will need a lot of additional code which also will utilize the CPU. A well-written multi-threaded application usually will utilize the CPU better and will use less CPU time. The second myth is that threaded applications are more complex than single-threaded applications. Again, when you start adding the additional support code for multi-threaded simulation in a single-threaded application, the code starts to grow and the complexity becomes bigger than the complexity of multi-threaded application. The third myth is that threaded applications offer benefits only on multi-core systems. Again, that is not true. Even on a single core system, you will get significant benefits if you need to wait for slow device or slow process to complete while doing other tasks in a separated thread. What are the typical tasks we have to achieve when we are writing multi-thread application? We have to create thread, we have to control the thread by starting, stopping, resuming or terminating it. We often will need to wait for the thread to finish its execution if the logic of the application requires so. We also need to maintain locking of any shared resources between the threads to prevent collisions. We need to have signaling mechanisms to send notifications to threads, and we will need to update the user interface with information coming from the threads. There are a number of classes and functions in Delphi which can be used for developing multi-thread applications. Those include the tthread class, the tEvent and tSimple event classes, the tCritical section, tMutex, tSemaphore, tConditional variable CS and tConditional variable mutex, tMultiread exclusive write synchronizer, tthread list, the system tmonitor, the set of interlocked functions, and the synchronize method inside the thread class. Now with this knowledge, let's take a look at how we can convert existing application into a multi-thread application. We'll start with a simple single-thread application which needs to read a huge amount of data from file. Here is our application, and inside our start function we will loop and read large amount of data from a file. If we run our application, we can see that it is working, however, it is not responsive to any events. We have to forcefully terminate it if we want to stop it before it has finished the loop. We can fix that up to a certain extent by using the already mentioned process messages. If we run the application, I can start the application and it will respond. However, now I cannot close the application and I am in grave danger of causing by mistake infinite recursion. The application will not close until I stop it. Let's see how we can write the same application as multi-thread application. First, in order to create our thread, we have to declare class inherited from tthread, which is the class wrapping the thread object, and we have to override the execute method of that class, which will be the function that will be executed in the context of the thread, or the function executed by the thread. In the execute function, we'll have the same type of code. We'll loop and read from the file the large amount of data. We only need to periodically check if the thread is terminated, so we can exit when somebody clicks the stop button. We also have a synchronization which will allow us to update the user interface. We'll cover it in few minutes. Other than that, our code is identical to the code of the previous application. Let's run it and see how it works. You can see that our application is responding, and we can even close it before the thread has been finished. Obviously, we have a better behaving application and our code is not significantly more complex. Inside this loop, we also would like to update our user interface. Here is a commented line which matches the code we had in our single-threaded application. We have a problem. We're trying to access user interface item, in this case a progress bar, from inside a separated thread. That is something we should never do in Windows application, since user interface items are not thread safe. Which brings us to the next topic: accessing user interface from a thread. Whenever we want to access user interface items from inside a separated thread, we need to synchronize with the main thread. Only the main thread in Windows applications is allowed to access any user interface items, so any such access has to be executed in the context of the main thread. There are a number of ways to do that. The first is to use the synchronize method of the tthread class. The second is to use shared data and send or post messages to the main thread. The third, and the one which I most often recommend, is to use a timer for periodic user interface update through shared object. Now let's switch back to our application and see how we're updating our user interface. We first will use the synchronize member function of the tthread class. This is the easiest way to update the user interface. However, it's a very inefficient way of doing so, and we should avoid using it whenever possible. Here is how to use the method. When we call a function, we pass as parameter another member function that needs to be executed in the context of the main thread. In this case, this function will simply assign a temporary member variable as current position to our progress bar. So first we'll assign value to our member variable. We'll call synchronize. Our thread will be suspended right here, waiting for this doSync function to be executed in the main thread. When the main thread finishes executing the function, our thread will resume and continue execution. This is exactly the problem with using synchronize. It causes the thread to be suspended while we are waiting for the main thread to update the user interface. Here is a better way to update our progress. In this case, we'll post a message to our window, and as one of the parameters in our message, we'll pass the progress information. Then we'll implement a message handler function which will handle our message, and we'll update the position of the progress bar in that function. Let's see the application running. It's obviously working well. Sometimes we need to pass more information than single integer variable. In this case, we'll use critical section. which is simple locking mechanism. The critical section is a special object which only one thread can lock at a time. The critical section has enter and leave functions. When one thread has entered the critical section, no other thread can enter it, so all other threads will be blocked waiting if they try to enter the critical section until the critical section is released by the thread holding it by calling leave. In this case, we'll assign a member variable with the progress information we want to update. We'll post our message, and inside our message handling routine, instead of using the W parameter from the message, we will update the progress from our member variable. Obviously, we can have more information than single member variable. Again, the application is working well. Finally, we will implement the same application by using timer to update our user interface. We also will use the interlocked set of functions to update member variables instead of using critical sections to demonstrate how those functions can be used for the purpose of exchanging data between threads. The interlocked functions guarantee that the exchange will happen in the context of a single thread and no other thread will interfere with the exchange of data. In this case, we are exchanging the progress data, which we passed as a variable, to our fProgress member variable. Inside a timer, we will update the position of our progress bar with our fProgress member variable. By using this mechanism, we can update the user interface not all the time, but instead with a specific period of time by the timer, thus reducing the utilization of our CPU. Let's start the application and see the result. Again, the application is working well and we have less CPU utilization since our user interface is updated less frequent than in the previous examples. We already saw examples of using locks in our applications. The next question is when we need to use those locks. When multiple threads read from a resource, there is no conflict and there is no need of locking. If one or more threads try to modify a resource while other threads are reading the resource, there is a conflict and we need to protect the resource. When multiple threads try to modify a resource at the same time, there will be a conflict. What resources need locks? Boolean variables, due to their nature of having only one of two possible values, do not need to be locked. Any other shared resource, be it a variable, class, object, or structure, needs to be locked. On multiprocessor or multi-core systems, there is no guarantee that anything other than Boolean will be processed as atomic operation, and even byte is not ensured to have the same value while the processing is happening. Locking and type of locks. Conflicts are resolved through temporary locking of the resources. There are number of locks which could be used, a number of locking mechanisms. There is the semaphore, the mutex, the critical section, the more complex multi-read single write lock, the interlocked set of functions which we saw being used earlier, and the conditional variables in Vista and Windows 7. When we use locks, we run the danger of mutually locking two threads. This type of condition is called deadlocking. Deadlocking occurs when thread A has acquired lock 1 and tries to acquire lock 2, and thread B has acquired lock 2 and attempts to acquire lock 1. In this case, the two threads are deadlocked. We will demonstrate deadlocking with our next application. Here we have a message structure. We have queue of those message structures, and we will have number of threads, each of them containing such queue inside. Here is our array of threads. Inside our thread execute, we'll first lock the queue associated with the thread. Then inside a loop, we will lock the structure of another thread. we'll copy data from the queue belonging to the thread to the queue in the other thread. Then we'll unlock the queue of the other thread, and we'll repeat that for multiple threads. Finally, we'll unlock the message queue, and we'll update the user interface using a new feature introduced in Delphi 2010, anonymous functions in synchronize method. This is not the most efficient way to update user interface. However, we can use it here for demonstration purposes only. If we run the thread, after a while it's gonna lock. If we suspend our application, we can see that a number of threads are locked by each other. We have only one option to kill the application. We just demonstrated deadlocking. To avoid deadlocking, there are certain rules we can follow. The first rule is to acquire locks in the same order from all threads. That is, however, not always possible, including in the case of the application we just demonstrated. The second option is to keep locks by only one thread at a time and to unlock it immediately before we have acquired another lock. The next rule is to keep locks for as short period as possible. And finally, in order to actually achieve the previous rule, to use the data for long periods of time, we should first lock the data, make a local copy as quick as possible, release the data, and then slowly use our local copy, in essence implementing a local cache. Now let's see how we can apply those rules to fix our deadlocking in the application. All we need to do is declare a local copy of our messages, lock the queue, make all necessary quick changes into the queue, make a local copy of the queue into our temporary storage, release the queue, and only then start locking the queues of the other threads. That is all that was needed to fix our deadlocking for good. Let's run the application and see it working. No matter how long we keep this application running, there will be no deadlocking. There are other multi-threading synchronization tasks needed to be achieved beside locking. Those include waiting for thread to finish, notifying the threads by sending events including kernel events from driver and devices, and waiting for multiple objects including events and threads to be signaled or completed. We often need to send notification from one thread to another. For this, we have a number of choices. We can use events to notify one thread from another. We can send messages, usually to the main thread. We can use conditional variables if we have Windows Vista or Windows 7, or we can use shared resources or variables to send information between the threads. Now it's time to see a more complex example of multi-threaded application utilizing some of those functionalities we mentioned. In this application, we will have number of threads reading data. We will have one thread writing into the same data every now and then. We will use a new type of lock called multi-read exclusive write synchronizer, or multi-read single write synchronizer, as is commonly known. We'll also still use critical section for updating our user interface. We'll also use event to start our writer thread. We'll start by examining the code of our writer thread. Our writer thread will wait for event which we have created. The event will be auto-clearing event, non-manual clearing event. Whenever we need to wake up our thread, we will signal that event. The thread will stop on the event if the event is cleared, which is the initial state of the event. Whenever we signal the event, which will happen from inside a button click, the thread will lock the data for writing. If the data is locked for writing, no thread can read the data. We'll update the data and then we'll unlock it for the reader threads. the reader threads will do nothing other than just reading the data into their own local storage, which they will lock temporarily. And finally, our main thread inside a timer periodically will go through all of the threads, lock temporarily their data, make a local copy as we have recommended earlier, and after that update the user interface. Let's see the application in action. Let's fire the writer thread and generate some random data. Now all the threads are reading from that random data. We can randomize number of times. What is the advantage of our multi-write single read? The advantage is that now the reader threads will read the data simultaneously without locking each other, which means multiple threads can read the data at the same time. This type of lock prevents only writer thread to modify the data while the reader threads are reading it, and vice versa. But the reader threads are not mutually excluding each other. We also probably should take a look at few other functions. This function forces the thread to be terminated. This function will wait for the thread to finish its termination, and of course once the thread is terminated we can delete the object associated with this thread. Our application is well written, however there are a number of problems. What if we forget to lock the data before we access it, or if we lock the data and then forget to unlock it from inside a thread? Our application will definitely misbehave in the worst possible way. There are ways to architect the application to reduce the number of such dangers, or often even completely eliminate them. The solution is, instead of accessing the data directly from inside the threads, to wrap the data in a class to protect all of the content of the data, and then create interfaces which will interface our data through access objects, which automatically will lock and unlock the data and will provide only locked access to the data. In this application, I have declared a simple locking interface which has read and write mechanism, and inside the constructor of a class that implements the interface, I will be locking the object. In the destructor I will be unlocking the object. The same goes for our write data implementation. I have also created such class for our critical section. So here in the constructor we'll enter the critical section, in the destructor we'll exit the critical section. Now it is very easy to make sure that the data is always properly locked and unlocked. As example, in our writer thread, when we want to update the data, we'll first obtain interface to our data, then we'll work with our interface. For the duration of the existence of the interface, the data is locked, and at the end of the function, the data automatically will be unlocked. And we will do the same for our reader threads, except in this case we'll obtain reader interface. We will do the same for locking our local data. And finally, inside our timer, when we want to create a local copy of the data, we'll use a small helper function which will create interface to the thread data. We'll obtain that interface which will lock the data. We'll make our local copy. The data automatically will be released, and then we can use it to update our user interface. This application makes sure that we will not corrupt data by mistake, and we will not forget to unlock any locks. This application is architected for multi-threading from the ground up. Here is our running application. This demonstrated that it is always a good idea to architect your application with multithreading in mind. Here are some examples of multithread architectures. Typical cases include dedicating threads to communication, be it serial, USB, or network communication over sockets, using threads for slow background processes, such as reading from hard drives or processing images, isolating threads in component classes for dedicated purposes, such as image processing classes or components, splitting tasks between threads to utilize multi-cores or multiprocessors. Typical case is a multi-threaded for loop. In this case, each particular loop will be executed in a separated thread, in essence in parallel, speeding up the loop execution. Separating the application by thread per task to utilize multi-core, enclosing shared resources and the logs in classes, and creating thread pools to reduce the create-destroy time for threads. In essence, instead of creating new threads each time, just pulling a thread from the pool and resuming it and suspending it after the thread is no longer needed. Debugging multi-thread applications, it is always a challenge. However, Delphi XE allows us to name threads to make it easier for us to debug them. It allows us also to put thread-specific breakpoints. It's also a good idea to add thread context information in the logging in order to allow us to trace the logging information back to a specific thread. Here in one of our applications, we can see how easy it is to assign name to a thread. All we need at the beginning of the execute method of the thread to call nameThread for debugging function. If we run and suspend the application, we can see that our threads have more meaningful names than just some number. Up to this point, we are showing multithreading as it is known today, simply running multiple threads in the context of the same process. However, the industry is evolving and we have more and more complex architectures which can employ the same type of approach as in multi-thread applications. We have massive multi-core systems with 8, 16 and more cores. We have multiprocessor systems with 2 or more processors. Now, in addition to CPU, we can also utilize the GPU for parallel processing. GPU now officially stands for General Purpose Unit, and we have APIs such as CUDA or OpenCL, which allows us to perform general purpose tasks on the GPUs. We also have cluster supercomputers, including the IBM Roadrunner. We have grid computing. We have server farms where multiple computers are connected into a network to work on the same task. We have cloud computing, which in essence is distributed computing over the internet. We also have peer-to-peer computing, including the Boeing SETI-at-Home network, which in essence performs multi-threading processing over multiple computers in peer-to-peer network. Here is how affordable today's supercomputing has become. The Nvidia Tesla GPU, as example, comes with 960 cores for only $1,300, and it is capable of processing 4 teraflops per second. Here is one example of computer farm at CERN, and here is an image from the IBM Roadrunner cluster supercomputer. Here is another example of Silicon Graphics cluster supercomputer working for NASA. Thank you for listening to my session. My name is Bojan Mitov, the president of Mitov Software. Here is our URL, www.mitov.com. We have products for video processing, audio processing, digital signal processing, computer vision, data visualization, visual instrumentation, and artificial intelligence. We also maintain 2 open source libraries. The OpenWire library available at www.openwire.org and IGDI Plus available at www.igdiplus.org. I hope you have enjoyed the session, and now it's time for questions and answers.